This is Geometry, Day 5, using similarity polygons, Part B. Something to remember, we talked about how dilation changed the size of an original polygon into an image. And we did that by multiplying the coordinates by the scale factor. What we're also going to talk about today is that the perimeters of similar polygons will follow that same scale factor as the sides do. So what this says is if two polygons are similar, then the ratio of their perimeters is equal to the ratio of the corresponding side lengths. This points out that if these two quadrilaterals are similar, then you can do the perimeter of one of the quadrilaterals with the perimeter of the other quadrilateral, and when you reduce it, you're going to get the same thing as if you just worked with one set of corresponding sides. It reduces all the way down to the exact same thing. And you could even fit in a last set of sides because this is a quadrilateral. And it's going to equal the same ratio as the corresponding sides do. Let's see that in action. So we're going to take the points. The points may or may not be on your grid already, so you'll plot those out. We can connect the lines between them. And place in our letters that represent their points. So we have K, we have L, M, and N. So we're going to find where this other quadrilateral shape is. It's P, Q, R, and S. We're going to figure out its coordinates by multiplying by our scale factor of 1/2, like we have earlier from a previous lesson. So to figure out point P, since the scale factor between these two shapes is 1/2, we're going to multiply the 2 and the 4 by the 1/2 and get 1 and 2. So we'll come over and plot that point 1, 2. Then we'll take the points 2 and 10 from the L and take half of each of those, which is 1 and 5. For point R, we'll take half of 10 and half of 16 to get 5 and 8. Plot that out. And then our final point, point S, we're taking half of the 10 and half of the 4, which is 5 and 2. Now we can connect those, and you'll see that we have a new quadrilateral, and its points are P, Q, R, and S. If we were to take tracing paper, we could see that the tracing paper shows that the angles are congruent. So if we come here and trace out our quadrilateral, we should be able to slide it over and show that those two quadrilaterals have the same angle. So Q and L are congruent. R and M would be congruent. You notice that the sides match up, so those angles match up. And of course the 90-degree ones are going to match up also. So that's just an easy way to indicate that the corresponding angles are congruent. Let's look at the side lengths. We're going to look at side KL. KL is vertical, and we can count the distance between there, and we see that it is 6. LM is slanted. Since it's slanted, we need to use a distance formula. The distance formula, which would be good to have ready for your midterm and your final exam, would be x squared minus, or x2, sorry, minus x1 squared plus y2 minus y1 squared. Well, the points that we're using for L is 2, 10, and M is 10, 16. So when we plug those in, this is going to be our x1 and our y1. This could be our x2 and our y2. So the length of LM is going to be equal to x2 minus x1 squared plus y2 minus y1 squared. That leaves us with 8 squared plus 6 squared, which is 64 plus 36, which is the square root of 100, which is 10. So its length here would be 10. MN is vertical, so we can count the units all the way up from N all the way up to M, and we'll see that that is 10. And KN is a length of 8. Now if we come on over here to PQ, we can see that PQ is 3. We could do the distance formula for QR. Our distance for QR, we're using Q, so the point Q has an X value of 1 and the R has an X value of 5. You just have to be consistent if you go in that order. So the Y value for Q was 5 and the Y value for the R was 8. So that gives us -4 that's squared, and gives us -3 that's squared. That's 16 plus 9, which is 25. The square root of 25 is 5. You can see that RS, you can count that down, and that's 6. And PS counts across as 4. Now it may not be much of a surprise to you, but we took half every time. But I didn't want to just use that scale factor right now. I wanted to be sure that we had an opportunity to test that scale factor. We actually measured each of the units. Now let's see what happens when we do our ratios. So when we look at PQ, PQ is 3 and KL is 6, and of course by dividing by 3 to both of those, we get that to be 1/2. QR was 5, LM was 10. By dividing by 5 for both of those, because that's the largest number that goes into both of those values, we get 1/2. SR and MN, we could divide those by 6. We get 1/2. And PS and KN, what's the number, the largest number that goes into both of those values? So we can divide both of those by 2, and you'll see that that's 1/2. Sorry, not 2, huh? That'd be 2/4. The largest number is actually 4. If you got 2/4, then you could divide it again by 2, and that would go down to 1/2. Nice job for noticing. So next, since the corresponding sides all have the same scale factor, that's enough right there to show that the two polygons, the two quadrilaterals, are similar to each other, because their corresponding sides have the same ratio and their angles are congruent. The corresponding angles are congruent. Next, we're going to look at the perimeter. So we're going to add the PQ plus the QR, the RS, the SP all together. And when we do that, we get 3 plus 5 plus 6 plus 4. That gives us 18. When we add our 6 and the 10 and the 12 with the 8, we get 36. And notice that we can simplify here also. If you notice, 2 goes into both of them, but it also 6 goes into both of them. Also 18 goes into both of them. So it really helps if you put the largest number in, and that ratio matches the ratio of the sides. The ratio of the perimeters is matching the ratio of the sides. So at the bottom of your page, if 2 polygons are similar, then the ratio of their perimeters is equal to the ratio of the lengths, of the side lengths. They have to be the corresponding side lengths. So we looked for the corresponding parts and we reduced those, and we got halves every time, and we took the perimeters and we reduced those, and we also got a half. That's not a coincidence. That will always happen with similar polygons. On the flip side, we're going to look at trying to find the perimeter with triangle Wxy. There's really 2 methods for doing this. You could take triangle Wxy and try to calculate out what the missing sides were, write 2 sets of proportions, solve them both, and get your 2 different answers. Or we can take the scale factor the way it's written and use that scale factor with the larger triangle's perimeter to calculate the smaller triangle's perimeter. Let's see what the corresponding sides would be. I know that Wx is 40. So Wx is the first 2 letters. Which side does that correspond to for the other triangle? It should correspond with the first 2 letters also. First 2 letters go with first 2 letters. That's the special part about a similarity statement. So XW, or Wx, goes with PQ. And that's 40 over 72. You might notice what numbers go into that. If you keep reducing it, you'll take it down to 5/9. So that's our K value. That's your scale factor. Now, with that scale factor, I'd be able to take the perimeter of the side that we see, the triangle that we know, and I'm going to write a proportion. Now, did that 216, which triangle did that come from? That came from the triangle that's larger. That came from the triangle with the 72. So I see that it came from the triangle with the PQ on it. So that's on bottom. So my 212 must be on bottom. On a test, that could be a little tricky, not remembering or noticing where your unknown value goes. It does not always go on top. You have to pay attention to what values you're working with. So now we're looking for the perimeter of triangle Wxy. So to do that, we're going to cross multiply. And really, in this case, I only have to cross multiply one direction. It doesn't really help me to bring the 9 over and then divide it away. So that's going to come out to be 1080 divided by 9 equals the perimeter of triangle Wxy. That's just kind of shorthand. It's not a formal way to show perimeter, but it's working for us here. And this reduces down to 120, and that is the perimeter of triangle Wxy. So notice, I didn't find the individual sides. I could have, and that would have solved it and figured out the perimeter also. I used the scale factor between corresponding sides to help me calculate the scale factor of one of the triangles. For letter B, we look here, and we're supposed to find the measurement of QS. What type of segment is QS? If you look back one day, you'll notice that QS is part of the triangle that goes from a vertex to the opposite side. It touches the opposite side in exactly the midpoint. So by turning your notes back, you'll see that if you go from a vertex to the opposite side and are perpendicular, that's called an altitude. But if you go from a vertex and touch the midpoint, so the tick marks really show you that it's halfway, that is called the median. So we're looking for the median. And that was the hint they gave us up in the directions. This is called a median. And what's the length of that median? Well, first we need to find the scale factor. So two corresponding parts, 16 and 24. They can be reduced. Looks like 8 would go into both of those. And that's 2/3. So if that's 2/3, then I know that the medians of the two similar triangles are also following the same scale factor. So 2/3 is going to equal SQ over 39. Now I put the 39 on bottom because it came from the bigger triangle. It came from the triangle that had the 24. Since the 24 was on bottom, I had to put the 39 on bottom. Since the 16 was on top, I had to put the QS on top. Then we could cross multiply. Again, I only had to cross multiply one direction because that left me with my QS all by itself. Now we see that QS would need to be 26 in this case. For our next question, we have two basketball courts. We have an original basketball court and we have this new one. The larger cement court is being poured for a basketball hoop in place of a smaller one. The court will be 20 feet by 25 feet. So let's try to draw a picture of the larger one. So we have 20 feet for the width and 25 feet for the length. We have a smaller court. It's similar in shape. Not similar as it kind of looks the same, but it's similar in terms of geometry. The angles are congruent, the sides are proportional. But it was only 16 feet wide. So we have a smaller original size court where W equals 16. We just don't know what the length would be for that one. So that's part of the questions that we'll be answering here. First, we're going to find the scale factor of our new court to the old court. New to old. Image over original. Scale factor is always new to old. Image over original. So the image value that we know for sure is 20, and the original shape that we know, or length that we know for sure, is 16. To find a scale factor, we like to reduce that as much as we can, and that takes us to 5 over 4. 4 over 5 would be incorrect. 5 over 4 is correct because it's supposed to be image over original, which was the new court to the old court. Now we'll be able to take that scale factor and help us calculate for the missing side. So our 5/4 is going to help us calculate out what our missing side length is. Well, we're looking for length. So 25 over L. Notice where I put the 25 this time. I didn't just put it on bottom where most of the other times we've been placing it, because it's got to follow the pattern of what your scale factor is made of. The scale factor was image over original. The image is actually what we know what it is. The original is what we didn't know. The original was on bottom, so the unknown is on bottom. So we're going to cross multiply. In this case, I'm going to cross multiply both ways. 4 times 25 is 100. And I can get the L simplified and calculated by calling it 20. So the length of the original court was 20 feet. We could make a chart following that. We have the old shape and the new shape. We have wide. How wide is it and how long is it? The new shape was 20 feet wide and 25 feet long. The old shape is 16 feet wide and 20 feet long. If you look at it in this format, it pretty much sets up the proportion for you. So sometimes making the grid, seeing a grid in this format, helps you solve for an unknown value. And you're just ready to cross multiply, or reduce first and then cross multiply. So let's come on over to the new court. We're going to find the perimeter. Well, there's a formula for a rectangle perimeter, and that's 2 W's because there's 2 widths in a rectangle and 2 lengths in a rectangle. So the formula to calculate perimeter is 2 times W plus 2 times L. W, of course, was 20, and L was 25. So that's going to come out to be 40 plus 50, and the perimeter of the new court is going to be 90. And that should be 90 feet. Now, to calculate the perimeter of the older court, we have enough numbers now, we could just add them all up. But they're asking us to do it using the proportion. What's the scale factor? Do we know a scale factor between corresponding sides? That's what the 5/4 was. So using 5/4, we're going to make a proportion out of that. The other perimeter that we know is 90. Which figure did the 90 go to? Does it go on top or does it go on bottom of our proportion? The 90 was part of the new shape. It was the perimeter of the new shape. The new shape was on top, so the 90 has to go on top, and our perimeter of the other rectangle, the smaller one, the original court, will go on bottom. So we'll cross multiply. Divide by 5. And the perimeter of the old court was 72. And that was feet. Example 3. In our diagram to the right, we know that triangle BCD is similar to triangle RST. If they're similar, we know the corresponding angles are congruent, and we know the corresponding sides can all be reduced down to the same fraction. So we need to look here and try to figure out what set of sides that we're going to match together. We couldn't use the 13 because that corresponds with the x, because CD corresponds to ST. But we could use BC and RS because those are both the first letters. So that's 12 over 24, and those looks like they can be reduced. Or we could also use BD over RT. BD is the first and last, RT is the first and last. We're going to divide, and we also get that same scale factor. That's not a surprise. They should be. If they are similar to each other, the corresponding side lengths have to reduce down to the same thing. So now for us to solve for x, we're going to take that scale factor, or the bigger numbers if you need to, but scale factor works the best. And we're going to fill in and solve for x. And to calculate x, we need to know what side that corresponds with. X is on side ST. ST corresponds with CD. So if XT, does that go on top or bottom? Does the X go on top or bottom in this case? Well, ST is the bigger triangle. It came from the bigger numbers. It goes on bottom. So the X is going to be the bigger number, and 13 is going to be the smaller number. I can cross multiply, and X equals 26 feet.